Thank you, Jim. Good morning, ladies and gentlemen. Just from the outset, as Jim said, I'm a climate scientist. I'm not a lobbyist, and I actually don't have very strong ideological views on the politics of what I call global warming. But as you all know, the whole global warming industry is just totally contaminated by politics and ideology. But I try as best I can to stick to the science. And I'll try to do that this morning in half an hour allotted to me. But I'll try and do this in as simple and non-technical a way as possible. It's easy to get bogged down in the technicalities, and hopefully I'll cut through some of those technicalities and explain what I think is happening in climate science research, in the climate science research camp, and what the implications might be for policy beyond the 2012 Kyoto threshold period. Of course, the implications or the ramifications of these developments are up to people like yourself and the community. As a climate scientist, I'm often asked, and I often speak, or have frequently spoken to boards of directors of big corporations, and I'm often asked by them, what will the global science drivers be on emissions policy on 2012 and onwards, that is the 2012 outside limit of the Kyoto Protocol. If there are developments that are significant, of course, it will have an impact on emissions policy, because if it reinforces a concern, there will be added incentive and enthusiasm for promoting emissions policy, vice versa. If the science shows that there is in fact less of a problem or none of a problem, then of course the reverse will happen. Clearly then corporations are looking to plan within that 30 to 50 year time horizon. They're making big investments, some of them multi-billion-dollar investments over that period. So they wanted to get a feel for the science's developments and the implications of this on politics via the various constituencies in certain developed world. So the question then specifically, will climate change policies continue indefinitely, even though we know that some of these initiatives for policy are stumbling, not in New Zealand, we're well ahead of the crowd there, we go where angels fear to tread. But there are lots of countries, and Australia is one, the United States, and several others that are proceeding very cautiously. China and India, of course, have really taken time out. So, if in fact the science suggests that the future possibilities of impacts due to human action on the atmosphere is more serious than we think now, then of course the policies will continue and become more onerous for business. If, however, scientific thinking is changing or might change into the future, the impact on global climate might be seen to be less significant and dangerous than we previously thought. So depending on the research findings, there could be a gain of confidence in what we see now, boost in concern, if you like, or the opposite. A lack of enthusiasm or a realization that we were, it was a sort of chicken licking type situation, a scenario we're in. So what I'm going to do is try to explain briefly where we are now, scientifically speaking, and secondly, where the science is heading. The second bullet point is going to be a little more challenging, but hopefully I can give you some snippets of what these developments are and make my point that way. So, getting underway, this is how we'll go. I'll look at where we are now, and then deals more fully with where we're heading, the uncertainties. Keep in mind what we're dealing with is that we're dealing with a situation where carbon dioxide is a greenhouse gas. Its concentration is increasing, and the arguments are very solid that the reason why they're increasing is partly due to humans taking carbon out of storage, fossil carbon, and putting it in the atmosphere. And most of this is, as you know, from burning fossil fuels, even though there's some other sources. And this can lead to global warming. If you change the gaseous content, trace gas content of the atmosphere, you're going to change the climate. There is no evidence that it will be a significant change, but everything we do has an impact on our environment. So where we are now may seem straightforward, but as you'll see in a bit, it's really not. And then where we're heading, this is the the issues of if there's warming, how much is due to us, what will be the significance of this, will it be large or not, and what is actually happening naturally, can we differentiate? So this is how we'll go. So where we are now. What you often find in the global warming debate, as I call it, is people appeal to authority. I present a scientific argument, and the respondent will say, or the debater will say, well, the IPCC says, or Tony Blair says, or some authority, Al Gore says. People appeal to authority all the time, which of course is not scientific. You should stick to the facts and to the arguments. But the IPCC is seen as the infallible authority. So I thought, if we can take direction from them, we get a good picture of where we are now. So the most recent IPCC report, which was the fourth assessment report, said most of the observed increase in globally average temperature since the mid-20th century is very likely due to the observed increase in anthropogenic greenhouse gas concentrations. And this is often quoted verbatim. They define very likely as 90% probability, but they also state very clearly that this is a judgmental estimate. It's a bunch of people like us now saying, well, what do we think the likelihood is? Is it 80, 70, 60, 90? That's how it's decided. It's not a valid measure of uncertainty in a scientific or statistical sense. It's guesswork. Now, if you're going to use guesswork of this order of uncertainty, if you like, to drive very, very expensive policy, you need to be very clear-headed and confident about what you're doing. A colleague of mine calls this statement crawling with reservations, and that's what it is. It's most likely. This is after billions. The U.S. government in the last 10 years spent $60 billion in climate research. It's a lot of money. And in 4 assessment reports bring together the scientists from all over the world. We still are, I'm not sure. In fact, I was involved in the 2001 and 2004 ICCC reports, but then ran out of steam, as a lot of us do, just to bog down in politics. But that was the most recent report. In the third assessment report, which I was involved in, another quote from this. The fact that global mean temperature has increased since the late 19th century and that other trends have been observed does not necessarily mean that an anthropogenic effect on the climate system has been identified. Climate has always varied on all time scales, so the observed changes may be natural. It's not me saying that, it's the IPCC. This is a direct quote from their report. Okay? So if you are a green lobbyist saying, you quote the IPCC as saying that they are the ones that are saying that dangerous climate change, this is not true. They just don't know. In the first assessment report, even more blatant, global mean surface temperature has increased by about 0.3 to 0.6 degrees Celsius over the last 100 years. The size of this warming is broadly consistent with predictions of climate models. This is the last time they used the word predictions. That word was banned in all the subsequent reports. But it is also the same magnitude of natural climate variability. So if we are, they're saying, the implication here is if we are, as human beings, having an impact on the climate, it is nothing. It's within the range of natural variability. That is not more or less dangerous than what we actually see. And climate actually doesn't vary much. It's weather that creates the impacts of flooding, droughts, high winds, and so on. So very sober and reserved statements. The third assessment report, 2001, also said in section 14, in climate research and modeling, we should recognize that we're dealing with a coupled, non-linear chaotic system. And therefore, the long-term prediction of future climate states is not possible. Okay, no one at all, not even the great good IPCC, has made a climate prediction. And though if they attempt to even a projection, they are full of uncertainties to the point that it is totally useless driving policy. And this IPCC says that too. Their information is not good enough to drive policy. So where we are now, even with the IPCC taking an authority as opposed to anyone else, we are still in the dark, and we need to turn a few lights on before we commit ourselves, I think, to priorities in environmental concerns that in fact might put others more important ones, such as clean water, sanitation, healthcare, education for billions of people. I put that ahead of all those things. And what happens in the IPCC, because it has an ideological component, they tend to massage these things. This statement actually occurs at the very, very end of the report. But I always start my lectures at university from the end of this report and move back. So what we've got is a situation where we are now. And this is not supposed to be disparaging, but this is where we are, scientists such as me. It's not ICCC, we are the contributors. But predictions of future climate are not possible. It's just speculation. All that we have is speculation. They come from global climate models that have not been verified, so the output is merely conjecture. An output from a climate model is worth nothing. It's a hypothesis, it's speculation. So by quoting the output of a climate model and say it'll lead to extinctions, it'll lead to this, it'll lead to that, it's wild speculation. It's of no consequence at all, and no sensible businessman or woman would make $1 million decisions based on speculation. That's why the IPCC insists on using firstly projections, then scenarios, now use storylines. So, before we move on though, what does the data say? Because of course in science, data is everything. So we should look to the data, and always look to the data. You have a hypothesis in science or a theory, and you look at real-world observational data to test that. That's science 101. Well, have a look at this statement, and often people are shocked by this. But this statement is true. There's not one single peer-reviewed research-based article that provides empirical evidence that human-caused emissions of carbon dioxide are causing or will cause dangerous global warming. And of course, I say real world, that's not data from hypothetical computer models. There is not one single peer-reviewed research-based article that provides empirical evidence that human-caused emissions of carbon dioxide are causing or will cause dangerous global warming. Now that is a very profound statement. Given all the hype and people are, why isn't there one single journal article? There's a chap in southeastern US, a professor of energy and engineering. He's offered $20,000 or $15,000, whatever. Anyone could send him one of these articles. Well, that's a fairly powerful statement, and it is 100% true. In fact, it makes you sit upright in the classroom and think carefully about what's been said. Nonetheless, you don't let this get in the way of a good debate. So what is actually going on? Well, take a look at this. What we have is confusion. While some would say, I know some at the Heartland conference in Chicago earlier, and some would say it's deliberate. And in fact, we have some emails that suggest it is deliberate, and I featured prominently in those emails trying to keep me quiet and put me down, and I think that's not nice. So there are it's not entirely honorable, but there are some people who are genuinely confused, people who genuinely are concerned with the environment, know that our track record isn't good, so their confusion is genuine. But if this is the case, and it snowballs, people are going to lose confidence in alarmist predictions. So in a sense, some good might come from all of this politicking, if you like, and exaggeration. Take the example of this graph here. This graph has been used a lot. It's used even in a publication that Bob Carter, Richard Lindsay, and myself, and some others did. Because we use it epitomizes the confusion and the problem. Even some scientists, in fact, there's a very well-known New Zealand scientist, controversial nonetheless, who uses this diagram not realizing what it says. And it's not even controversial about what it says. This is collected data from ice cores in the Antarctic. And it shows about 600,000 years of data, going to the present, which is the right-hand side. And the lighter line here is temperature from air trapped in ice core. So they're roughly correct. And this is the CO2 concentration in the air bubble trapped in the ice core, roughly correct, over 600,000 years. And it's for the Arctic, but it's a good record, or indicator, if you like, of trends in both temperature, air temperature, and CO2 in the atmosphere. And our good friend, Albert Gore, has used this. He's made millions of dollars for this. In fact, if Albert Gore was standing here, he'd be charging $120,000 in the US to speak to you today. But we'll not debate, we'll not even take advice from scientists such as myself, who are seen as unsympathetic. But he's used this graph. In fact, he used a ladder in his movie Inconvenient Truth to get up to here. Let's have a look at this graph just to show you the confusion and the malevolence that is involved here. If you look back in the past 600 to a million years, you notice that CO2 has gone up and down. And you notice where CO2 is now. It's much higher, according to this record, than it's been in the last 600,000 years. It's been higher 10 million years ago and so on. But we're looking at just this period. It's the period for which we have data. And you notice that CO2 is way up there. That's about 370, 380 parts per million. However, if you look back, the temperature at this present interglacial is actually lower than all the other interglacials. So even though our CO2 is way up here, we are cooler than all the other periods when CO2 is much lower. So immediately you think to yourself, well, hang on there. Why is Al Gore telling us this? Because it undermines his argument. Well, the reason why he was telling us this is that he was disregarding this fact shown by these green labels here. He was saying that if you stand back, you'll see that there's a sort of correlation, visual correlation between CO2 going up and temperature going up. But all scientists know, from Climatology 101, that this is a result of temperature driving CO2, not the other way around. And if you look at the data, it's about a 600 to 800 year lag. And what happens is, and this is well documented, and it happens even nowadays in shorter time scales, is that as the air temperature, as climate warms, the sea warms as well, and 70% of our Earth's surface is water. So water is the rule, not the exception. As water warms, it outgasses CO2. It's like a warm bottle of champagne. You open a warm bottle of champagne, it explodes and it's a mess. A cold bottle of champagne will stay unfizzy because it can hold a lot more CO2. And that's what happens as the oceans cool, they absorb CO2. And this is the process operating here. Nothing else. Nothing else. It has nothing to do with the radiative property of CO2 at all. Just our good friend Al Gore nearly became a president of the United States. Has messed it up. Deliberately or out of ignorance, there are juries out on that. So, back to where we are. Let's look then to where we're going. So the uncertainties. Let's look first at these. How much of any observed warming is due to humans? And if humans are to blame, how high will the temperature rise? So what has recent research got to tell us about these uncertainties? What does recent research suggest? Well, we rely on models in climatology a lot. I work with boundary-led climatology, and there's nothing wrong with that. Models are a way of moving forward. They can be useful, and we strive to use them, but they're very complicated. We can't predict. I can't tell you what the weather's going to be like next Friday, let alone climate in 100 years' time, even though we use very sophisticated meteorological models. But there are lots of problems, lots of limitations. That's why the ICCC came out clean and said that the models are really not useful for policy making. In fact, it's misleading. And the reason why is that these unknowns, and these unknowns are diverse and sundry, but the three main categories are the oceans, because our planet is, we're a wet planet. Someone said you shouldn't be called Earth, you should be called water. And it's very true. I always say to my students, don't think about land, think about water. Land is the exception. Just because we live on it, we give it high priority. The oceans are a big store of energy as well, and they're involved in evaporation of a lot of things. And in fact, greenhouse gases have virtually no effect on the oceans because of their radiative properties. The effect is on the air. Clouds and aerosols, but the big one is clouds. And you'll see I keep coming back to clouds. Clouds is in fact now the big thing. Clouds are the key element in this puzzle of understanding what's happening. And the reason why it's a key element is because of feedbacks. It's feedbacks. Feedbacks are everything. So what's a feedback? Here we've got a system. Here's a system, a baby in a pram, a very valuable system we would want to protect. Let's apply a change to that system. Assume I walk up to it and give the pram a shove with my finger. What will happen is the pram will move up the slide of the hill, roll back down, and eventually settle back where it was, and probably the baby will fall asleep. So that's a very good outcome. I applied a change, but the feedbacks then were negative, and it's a stable system. And in fact, all our teaching in climatology from the 60s onwards show that we are dealing with a stable system. So why would we think otherwise? The otherwise is this system. We apply a change, the same push to the pram, and of course, you get catastrophe. Depending on where the pram ends up, if it hits this tree here, the baby might not be in good shape. So a very serious outcome. Those feedbacks are those of an unstable system, where positive feedback effects occur. Now, if you're in a climate alarmist, you have to rely on this scenario. You can't rely on the other. So the onus is on scientists to show data that proves this particular scenario. And of course, this is what we're arguing. We're arguing about which of these two systems prevail. If you look back, this is a geological record. It's very proximate, but it's going back about 4.6 billion years. Down here, here's the present. Up here, zero time. Holocene is the most recent period. And we've got colder than the present to the left of this line, and warmer to the present on the right of this line. It's very proximate. We can see two things in this graph. One is that climate is always changing. You know, as my grandmother used to say, well, you know, Chris, when I was a girl, the weather was much warmer than this and dry. And I say, Gran, of course, it was either wet or dry, cold or warm. Climate doesn't stay the same. It doesn't, never does, has never. It varies on all time scales. And we can see proof of this. In fact, we're in a pretty cool period now. When the dinosaurs roamed, there was the Jurassic, Triassic, nice and warm, support large numbers of large animals. The other thing to look at, though, apart from the fact that climate's always changing, it's never run away. We never get a runaway effect. It seems to be coming back. It's like the baby in the pram. It's a stable system. It tends to recover, if you like. And the same thing applies at more recent time. This is taken from the ICCC, of course. I do that as much as possible. No one dares challenge it. And here you see, of course, the medieval warm period, much warmer than now, and Holocene maximum is significantly warmer. This is the last ice age which we're coming off. So this bar is this one here, and this group is this graph here. So we can expand this, but the truth or the patterns we've seen prevail. So what have we got? We've got an increase of greenhouse gases. Well, here's greenhouse gas CO2 in parts per million, going from about 285 to about 580, 590, 585 in fact. This is what it was pre-industrially. This is what it is now, about 380, 390 parts per million. This is what happens if you double it. This is what the basic physics shows, and there's not much argument about this. What is arguing what this figure is, and it varies from about 0.4. Richard Lindzen thinks about 0.6. Some people say it's 0.9. I've taken the biggest so that I'm not accused of exaggerating. In fact, this is smaller. So you double the CO2, you get a very small warming without feedbacks. So that's global warming. A very prominent outspoken businessman in New Zealand said to me, Chris, if that's global warming, bring it on. We could really need it in New Zealand. And the farmers are keen on this too. Of course, what you look at this graph, and really what is the problem is not increase of CO2, but decrease. Imagine if we did something to decrease CO2. This would be really down a slippery slope here. Cooling is not good. No one will argue that. That's wrong. So at the face of it, we don't have a problem. We have a problem if you can show, with good science and good data, that there are positive feedbacks. And as I said before, no one has. And if they had found it, you can bet your life we'd hear about it. You bet your life we'd hear about it. And they'll probably let me know by email, first person in the world. And this is not including feedbacks, remember? So then you can argue that if positive feedbacks are prevailing, then this could be significant, baby in the ground. Well, here, let's look at some of the models. Best we've got. So here's climate sensitivity in watts for doubling of CO2 down at the horizontal axis. And here's the temperature increase or change for doubling of CO2 from pre-industrial levels. If you use positive feedbacks, is what the UN does, you get these figures. So you get anything from 2 to 6. Well, you can name your figure. A model, you can, as someone said, give me enough data, and I can give me enough coefficients in a formula, and I can make a graph to an elephant. I mean, you can get anything from a model. But if you try hard, you can get with positive feedback warming as high as 0.5 for doubling, or as low as 0.2, as 2, sorry. With no feedbacks, as I said, it's around between 0.4 and about 1. I put it here because this is what a colleague of mine said we should do, go for the higher level. This is Willem de Lange in New Zealand. But with negative feedbacks, you notice you get a very small value. And the scientists in the world who are alive now, who I respect, like Richard Lindzen, Roy Spencer, and a whole lot of others, Douglas, Willis Eschenbach, they all go for a very, very low figure, something around about 0.4. That's for a doubling of CO2, not just a minor increase. So these are the sorts of things we're looking at. If this sort of thing is reinforced, this is not a good basis for very expensive, controversial policy. And this is the sort of reasoning. This is the sort of reasoning that people like Lindzen and Spencer and others have argued, even I have argued it in some research, some data that we've got. And what we're arguing is that plus means increase. We get an increase of greenhouse gases, an increase of air temperature, because greenhouse gases, CO2 is a greenhouse gas. It will slow the rate of loss of energy from the sun back to space. We get more evaporation, there's more energy around, more atmospheric vapor. And of course, atmospheric vapor is the mother of all greenhouse gases. Its effect is about 80-20. So water vapor is the main greenhouse gas. So that's what you look for feedback. And the main feedbacks I've hinted already, as you'll see, we're getting more is cloud. When you get cloud, of course, the reflectivity of the Earth changes. If you see a picture of the Earth from space, we're a cloudy, wet planet where moisture prevails, and that moisture is largely in the form of the atmospheric clouds, which reflect very effectively, as you'll see in the very final slide of the presentation. It's critical. Makes CO2 look like trivial. And of course, what happens is the sole source of energy for our systems is the sun. If you decrease solar radiation, you get a decrease of air temperature, and that is a negative feedback. And that's what these people are all showing. And this is what I'll try to show for some data I have as well, to add to the excellent work by Richard Lynch and Roy Spencer and these people who are outstanding climate scientists and are not at all alarmist, in fact, very sober, reasonable men. So let's look then at what we haven't looked at now. How much is due to natural climate change? So I've speculated on what human beings are doing, but how, if we are to identify what we are doing, we've got to separate it from what is happening naturally. So another tack is not to look at what impact humans are having, but let's look at the mechanisms of natural climate variability that drives climate change and see to what extent we can account for that change with natural processes. And if in fact they're the main drivers of change, obviously we're not a significant player in this. So why get your proverbials in a twist when in fact you're not actually having the effect to think on the environment? Put your money into clean water, put your money into healthcare, put your money into education, put your money into things that billions of people need, not a Western scale issue perhaps. And this is the motive behind it from a policy point of view. So this is our record. This is a record, the so-called instrumental record. Surface record going back as far back as we can. This is the Hadley Climate Research Unit data, which up until recently, up until currently, the ICCC uses, because prior to 1979, we've only had data at the surface. After 79, we had very accurate satellite data. A bit before that, we had good balloon data, but nothing beyond the 70s or the late 50s for balloon data. So this is IPCC's data. You can see we've had a cooling of about 60 years, cooling about early 19th to early 20th century. We had warming, global warming for about 30 years. But this wasn't due to CO2 because CO2 wasn't rising, so it can't be. It wasn't rising much. It's got to be something else. ICCC tells us it's the sun. Then we had 40 years of cooling, which of course was alarming. We had a cooling scare, lots of cooling scares. That's when I was at university, and we were all told prepare for the worst. The ice is coming. And then we have warming. Now this is the warming that we call global warming. This is the warming since '79. And now that's stopped too, so we have a question mark again. But this is the record. So what caused these changes? How can we account for the very small changes, tenths of a degree? Hey, if you want to argue about tenths, let's argue. Let's debate it, see what's going on. So, is it the sun? Is it humans? Is it nothing? Richard Linton says, and I agree with him entirely, it could be due to nothing. You put a pot of water on a stove, keep the heat constantly, you'll find that the bubbles behave chaotically. Sometimes they pop up and splatter, other times it tends to simmer. It's a chaotic system, and that's what our climate is. It's an internal variable. It's never constant. It's always variable. So you don't need anything to explain these. But let's try to be good scientists and try our best to identify a process or mechanisms, they call it, and then link it to what we think the mechanism is doing. You can't just say it's human, because it may not be. It certainly wasn't humans here, cooling. If it is, how? Likewise, warming, and you have cooling, warming. So lots of things going on here. Let's have a look at it. This is the global warming that we're concerned about. This is the last one, so we might focus on that. Well, if you look at the climate models, if you look at climate systems, this is what you're dealing with. You're dealing with a watery planet. The Pacific epitomizes this. If you go on Google Earth and zero in on the Pacific, you can get an image where you don't see any land at all. The whole hemisphere is water. The Pacific is massive. Giant ocean, of course, our backyard. We have circulation systems in this. One of the most important is the so-called Walker cell, discovered by Walker, British meteorologist based in India in the early 20th century. And it's a very well-defined circulation system, but going from east to west. The other thing to keep in mind in this area is that this Walker cell operates in the tropics. Now this area between about 35 north of the equator and 35 south is about 50% of the Earth's surface. Because of the shape of the Earth, a grid square near the equator occupies a lot more as you get to the poles. Of course, a grid square at the pole occupies no space at all. So this is where most of our space is. Projections like this give a false impression of area. The other thing about this is water, large area, and so on. And thirdly, it's bombarded month after month, year after year by solar energy. This area is always in surplus. Energy just coming down relentlessly every single day of the year. And of course, the water absorbs most of the energy. The question I always ask my third year students, why doesn't the water eventually boil? And of course, the reason is there are feedbacks. The closest Klaproth equation shows that there are feedbacks, so the water actually cools itself, evaporation. But this is what we're dealing with. So what has happened recently, people have actually been focusing on this as an indicator of global circulation. And you want to keep in mind that at the edge of this area, the descending edge is what's known as the Hadley cell. And unlike the Walker cell, the Hadley cell goes from north to south. It rises at the equator and descends at the poles, at the mid-latitude. So here's the Hadley cell for the northern hemisphere. And as it goes up, the air rises and descends. So this is the edge of this area here. This is this area here. So you have a horizontal, if you like, an east-west circulation system, which is the Walker circulation. And it's occurring elsewhere too, but this is the big engine room of the atmosphere here in the Pacific because of the size, and we have good data. And then, of course, we have the Hadley cell, which is going the other way. It's moving this massive amount of energy from the equator to where it's in perpetual deficit at the high latitudes. And I cut out here, here's a Hadley cell operating, and this is the main, if you know what's happening to Hadley cell, you know what's happening to global circulation. So it's critical. Okay, it's operating in both hemispheres, it's massive. And in our area, this area here, is where the action is. So here we have the Walker circulation shown here. And it's linked to what you all know about, it's El Nino. El Nino, we're going to the history, an interesting history of why it's called El Nino, the Christ child. But really what it is, when the system is what we call normal, or this condition, normal breaks down, we have what's called an El Nino condition. It's not as simple as that. What happens, the atmosphere tends to vary, and it varies from what we call normal, or La Nina. There's no such thing as La Nina, by the way, it's a girl child. In fact, in vernacular in South America, it means prostitutes. It's not a nice analogy. But you can see what happens with an El Nino condition, that circulation cell breaks down. But really what's important is this. This may seem a bit complicated, but this is a graph that shows what's happening at the equator, which is this line here. This is what happens normally. You notice that the Walker cell is existing, but the Hadley cell is a bit messy. In fact, really what it is, it's not strong. So this is the Walker circulation happening here, and this is the Hadley circulation happening here, up and down. But when you have an El Nino condition, the Hadley cell picks up in strength. So there's variability in climate, but it still happens that this goings on in the Pacific is a good metric or indicator for what's happening climatically. So if we get a handle on this, we might get a handle on what is happening in our climate, including temperature. And this is what we use. At Walker cell, we use an index called the Southern Oscillation Index. And it's simply a relationship of pressure at Darwin and that of height at Tahiti. The reason why we use this is both Tahiti and Darwin have a long pressure record. So it's favored, and we use this for your meteorology in New Zealand, in Australia. Everyone uses the so-called troop index, the standard deviation of this pressure difference. And this is a measure of the Walker cell, a measure of whether it's operating vigorously or not. When it's breaking down, it's El Nino. When it's not, it's a highly La Nina situation, vigorous, well-developed circulation. And remember, it's linked to Hadley circulation. So what the recent data did, they took some really good quality data from this period, 58, rather than looking at surface data. They looked at satellite data from 79 to 2008, and they looked at radiosonde data produced by the US. And for upper atmosphere, we're not interested in what's happening on the ground in a white box or an airport. We're interested in what's happening in the atmosphere. This is what we're trying to model. So we use balloon data and satellite data, very accurate data. And from this, you get a mean global temperature from this. So you're using good quality temperature data. And for the circulation, we use Southern Oscillation Index as a metric for circulation. In this period from 58 to 2008, there were some big events, especially volcanic events, that threw tons and tons of aerosols into the atmosphere that caused global cooling. We had to actually look at this and take these into account. But that's not a big deal, but at least we tried to approximate reality as best we could. And this is the data we got. I put in 3 graphs so you can see it in more detail. Here's 1958 starting off going to 1980, 1980 to 1995, up to 2008. So this is the detail. And you can see that the dark line, which is the Southern Oscillation Index, and the gray line is global temperature. Now, there's no statistics involved, and no fancy footwork, no balloons, mirrors, or smoke. This is just the data. It's been lagged 7 months, a 7-month lag, because it takes a while for the Southern Oscillation to, or to put it this way, the global circulation have an effect. It doesn't happen instantaneously. So it seems that anything between a 3 and 7-month lag works for 8 months. And you can just, by standing back and eyeballing this graph, there is a very good correlation or coherence of the Southern Oscillation Index with their mean global temperature. High quality data, the best we've got. It's not perfect, especially when volcanoes around. Look at Mount Pinatubo's eruption cooled the Earth by about 0.8 of a degree over 3 years. But that's much longer than that one eruption, so we're not sure what's happening there. El Chichon, you notice there's a cooling period here, it didn't get as warm as the index suggested. But quite interestingly, if you take the last period, 95 to 2000, there were no volcanic eruptions. Things were very quiescent volcanically. So this is a really good one to zero in on this last graph. So let's have a look at it. Here it is, the last graph. And isn't that amazing? 2 things happening there. One is that they're coherent. This is not statistically processed data. The Climate Gate email group were apoplectic when this paper was published and immediately started to try and debunk it. But you can't allow this sort of things to occur in the literature. It doesn't show that CO2 matters. So this can't be allowed. So what they did, they debunked it. They didn't allow us to respond to the debunking, which is unethical, however. And then what they did was they had focused on our way of determining what the lag period was. We used statistics that were sloppily used, perhaps, and that I accept. But in fact, we were just trying to find what the lag period is. We didn't actually process the data, and this data is unprocessed. It's there. Anyone can produce this graph. In fact, the lead author, John McLean, is happy to provide anyone who wants it. And it shows it's uncanny. And what is more uncanny than the coherence of the 2 data sets? There's no trend. If the CO2 was operating above this, we'd expect a trend to be apparent there. If there is a trend, it is very small. I'm not saying that CO2 doesn't matter. We saw it does matter. But if it does matter, it can't be done. So this is the sort of thing, if this gets a lot of publicity, you have to actually sit down and take a deep breath and decide if Kyoto's and Copenhagen's and so on really are high priorities, or whether we should in fact have a cup of tea and let's see what the science come up with in the next 10 or 20 years. So back to our data. Well, here's our data. We've seen it already, cooling. I've got the cooling missing here. But really what happened too, and again another event that is well recorded, in 1976-77, the Great Pacific Climate Shift, it was called. And the climate of the Earth, temperature-wise, just shot up. It was within about 3 months it went, warmed about 0.3 of a degree. And this has been put down to the circulation in the Pacific. The ocean is a massive store of energy, so if circulation upwelling or downwelling changes, it can impact greatly. And this great Pacific climate change is important because it creates what's called non-stationarity in statistical terms in the data. You have to use the data prior to 1976, it's separate post-1976. That's why a lot of the statistics they use are really quite inappropriate. However, this is a big event, and we see it. We'll see it in the SOI coming up. Now, this is the study period that I've been talking about, from about 58 to 2008. So we can zero in on this to summarize what I've just said. So here's the Southern Oscillation Index going for the study period from 1950s on the left to the present. Anything in red is showing a kind of El Nino condition, and anything in blue, the opposite, the other side, positive, is a La Nina condition. And you can see here that in 1976, things changed. You can see there's more La Nina conditions here, more blue, whereas here there's more red. You don't need statistics to do that, you can see that. And it's well documented too. We've put it down to another oscillation working on 30 to 48 time scales called the Pacific Decadal Oscillation. But these oscillations are really just named tags. They don't actually mean anything. You need a mechanism. So this is our SOI data. Okay, now here's our temperature data, which we've seen. So let's put them together. Well, the IPCC says this warming, a great warming period of 40-odd years, or 50, 60 years of warming was the sun. So, hey, sun is our friend. We're not going to worry about that. It's not CO2. We don't need policy for that. Well, let's look at our SOI data for the current period of warming, cooling, warming, or question mark. If you look here, the prevalence, a high frequency of La Niñas brings cooling. Okay, high frequency of La Niñas brings. You can apply statistical methods. Soon you do that, my good friends in climate research, you can get upset. So you just stick away from statistics, look at it descriptively. If you look at a period past the Great Pacific Climate Shift, you can see that the El Niño conditions prevail. And since 2001, 2002, we're not sure. Whoops, I'm going backwards. Who knows what's happened in this period here? Is it cooling? This last period? We don't know. It's a bit premature, but you can see what's happening. We had a lot of El Niños to start with. It's a lot of La Niñas and El Niño hiatus. And then we're back now to cooling. Our model, our statistical model, shows that we're going to have cooling, and it's what's happening. No one's taking any notice. They may afterwards. So this is what everyone's saying. I mean, it can be since 1998 we've got cooling. Well, it's not really cooling. It's kind of things. Put it this way: global warming has stopped. Was my point about this period here. Things have calmed down a bit, which means CO2 is taking a holiday at least for a while. Okay, let's look at the last part of the 20th century. To recap on data, we have this warm regime. You notice when we had warm years. Okay, it's a PDO index now. It's a clumping of these El Niño conditions. A cool regime, which we had global cooling, and then a warm period, which is global warming. Now we've got that cooling warming mix. So the findings we're finding, or the summary of this recent data, is not just by the work that we've done, but others as well. They keep coming now. There's been one recently in literature the last 2 months. That El Niño southern oscillation, because we have data, is a good metric for global temperature, because it's actually linked to global circulation, which of course is what these climate models are global circulation models. That's what I call GCMs, global circulation models, not global climate models. And SOI is a metric for this change. So if you get a change of ENSO, El Niño southern oscillation, and you apply a lag period, you get a good correlation. And with La Niña conditions, zonal circulation, Walker circulation is enhanced. Right? With El Niño, Walker's heavy circulation is increased. So you get one increases, the other decreases. And this is an explanation, or as we call it in the trade, a mechanism explaining what's happening. So this mechanism is happening, but really what is happening? And what is happening in my view is this circulation system, especially heavy, is affecting cloudiness. It's cloudiness that is actually the driver of the cooling and warming, not the movement of energy from the equator to the poles. It's this cloud cover. And some of the data, I'm trying to persuade my colleagues to look into this. If you look at just schematically, this is La Niña. You notice the clouds are confined over northern Australia and Indonesia. Once you get a breakdown, cloudiness patterns shift. And clouds are very, very important, very important. High clouds cause warming, low clouds cause cooling. So clouds are very important, and they're super important. They make CO2 look trivial. In fact, CO2 doesn't even have it can't work at the same order of magnitude as clouds. Clouds are massive. And here we looked at this data, recent data. This is total cloud cover for the Earth as a whole, in tenths, in percentage, from 70 to 63. And this is global temperature. And you notice a good correlation, not a high sensitivity one, but with more cloudiness, you get global cooling. So there's something there, and so we've got a mechanism, if you like, to explain this. But what is even more amazing is Pali and his group, in 2004, published a paper, and they continue to do it. It's a bit out there now. This group are amazing, published in Science in 2004. And this is what's called Earth's albedo, and albedo is climate talk for reflectivity. And you can see then that since the 985, the cloud cover has resulted in albedo dropping. So it was more solar radiation was occurring, was being absorbed. So you get warming. And look what's happening recently. The reflectivity is going up, we're getting cooling. This is very, very powerful data, because what it does, it shows you, gives you a mechanism to link the circulation changes. So the implications then, to round off, is a natural global force, natural climate forcing, due to mechanisms such as we see, Richard Linton calls internal planet variability, can account for a lot of what we see. We don't need CO2. We don't need to worry about things. To say it's CO2 and to run away and have a policy based on that is ignorant, in my view, and stupid at worst. So, there remains, as I started off, no real-world observational data that human-caused emissions of carbon dioxide are causing or will cause dangerous global warming. There isn't any, because we can see that natural mechanisms currently are very persuasively involved. Thank you.